Hello, Hong.
And you?
Is Martin here?
Not yet. We are waiting
I
for
should
Martin
tell
and
them because they don't know. I will forward the link again to them.
okay, thank you.
Martin. Hey, Hong, can you change the title for one song? It's a little bit embarrassing you call him professor. It's not yet.
I'm sorry. I thought that.
Just change to doctor. It's okay. Then you
Okay.
say Doctor Perrault. Okay.
Oh, that's okay. Yeah.
Send to them. I see. If Martin, you never know. If she cannot join on time, I can go first.
Yes, okay. Because according to the schedule, she will be the first one.
Yeah. Um, seriously, are you interested still in the university scholarship?
Yes, sure. If you have time, then we can just go ahead with
We
this.
can still use the old template and change a little bit. I'm happy to do, but what is the
Yeah.
plan? Two master, one joint PhD or whatever. We have to.
Yeah. I think we just keep the same. Then it how say the budget is okay for
Yeah,
one
yeah. The
PhD.
budget will be the same, huh?
Yes.
And the budget will be the same.
Oh,
Be
just one.
careful. Be careful,
I,
Ju, because
I
a competitor is listening to you.
Hey, but I win once already. Yeah, I have good basis. So you see it in different rooms now.
right, exactly. I just want to tell you that there are something coming up. We are now being quarantined because yes, that's the really the problem for us for the future to
Yeah.
tomorrow. Then we have to postpone to next week. We both have in the same floor. We have the F0, so on the floor is quarantine at the moment. So that's why today I am at home.
Okay. Yeah. Yeah. But keep all the DGTs in the fridge at 4
Yes,
degree. Yeah. So
yes, yes.
that's okay.
I did
For
it
I
immediately.
think maximum 1 month should be okay, but not
Very
longer than that. Yeah.
yes.
Yeah.
I will try my best to go as soon as possible.
Yeah.
Yeah, everything is better, and then we just go. Yeah,
Okay.
yeah.
And
Even
I think home, yeah, we don't like didn't hear what we are talking, so we will schedule a meeting
privately.
afterwards. No, I'm
Sorry.
joking. No, I also need to discuss with Hong about short initiative. Hello, Martin.
Hi,
Hello.
Martin. Nice
Hi,
to
hi.
see you.
How are you?
I'm happy you are here. Then I don't need to go first. You are the first.
Không có được. Không được. Chỉ có mờ đi thôi.
Martin, yesterday I have already gave the classic water sampling, soil, digestion, sequential extraction methodology, all the basic knowledge. Shortly introduce the DGT. So you may then continue about.
Hey, Martin.
Hello.
Hi, Martin.
Yes.
How are you doing?
Fine, fine.
At home, everybody is at home.
I can see the Christmas tree in the background. Okay,
We
it's
have
just
Christmas
around the
tree
corner.
here. And you have Christmas tree at home also, or not?
Yes, we have.
Yes. Ah, that's nice.
You celebrate?
No,
Really?
no typhoon in Vietnam.
For children, we separated it since we were in Germany, and we were keeping it.
Yes.
Yeah.
Only for your family. Okay. Yeah, because I think for Asian countries, Christmas is a commercial holiday, commercial festival, I think.
Yeah. Okay, I think it's time now, huh?
Yeah.
Okay, so let's see the people coming in. Anyway, it's time. So, thank you very much, all of you who are being here today. So we are in the second day of our workshop. So to go to the first presentation, I wanted to introduce to all of you Professor Martin Limakers. Sorry. So she's also in the same chair with Professor Yu Gao from Free University of Brussels, Belgium. So Professor Martin, can you please introduce shortly yourself and go ahead with your presentation? Thank you.
Okay. Thank you very much. So I am Martin Leermakers. I'm working at the Vrije Universiteit of Brussels. And I'm a biogeochemist working on aquatic pollution in riverine systems and in marine systems, and essentially working on trace metals and trace metal speciation. So this is one of the aspects which we will be discussing today. And this first presentation will be about the use of DGT to assess bioavailability of trace metals, of trace elements in general. So I will share the presentation. Okay, can you see the presentation?
Yes, we all see it.
Okay, perfect. So we'll give, you have had already a general introduction on the principles of DGT, but we'll repeat a bit about this and how it can be applied to assess the bioavailability of trace metals. This is actually one of the main strengths of DGT, and the application on the use of DGT to assess bioavailability has been increasingly popular in the last years. So in 2015, Zhang and Davidson, who invented this technique, also made a review article on the use of DGT for bioavailability studies. But since then, very many new articles have also been published on this aspect. And most of the aspects deal with the uptake of metals in plants, in vegetables, in wheat and rice, etc. But there are also studies on the uptake in periphyton and macrophytes, also in phytoplankton, and how metals can be limiting in the phytoplankton growth. Also some publications on metal toxicity to fish, and also some publications on uptake in benthic invertebrates. So a number of these applications I will also discuss in this presentation. So first of all, we have to know what is a bioavailable metal. When is a metal a bioavailable? So a metal is bioavailable when it can pass the cell membrane. And it passes the cell membrane through active or passive transport through channels which are specifically designed to for the uptake of metals. Also, the essential metals pass through these channels. And so the metals have to be in their free metal ion form to be able to pass through these channels. In water or in any aquatic environment, there will only be a very small fraction of the metals present as free metal ions. Most of the metals will be bound to ligands. These ligands can be inorganic ligands or organic ligands. So these ligands have to dissociate in their free metal form to be able to pass through the cell membrane. If these ligands can easily dissociate into their free metal form, they are labile metals, and then they will be taken up by they can be taken up through these channels. If we have very strong ligands, which cannot dissociate, then they cannot also pass through these channels, and they will not be taken up by the organism. So they will be non-bioavailable. So that's the essential aspect which needs to be considered. Also for elements which are in their which are present in the environment as oxyanions, such as elements such as arsenic and antimony, molybdenum. They can pass a cell membrane even if they are anions, but they use other channels. They use the channels for phosphate and sulfate. So there are just other channels in the cell membrane which are specifically designed for these anions, and they are used for these elements. Well, this is dynamic. Didn't remember that. So they have to pass the cell membrane, and then they are adsorbed by the animal and affecting the life cycle. Oh, sorry, I went too fast. So bioavailability is very complex. It's not as simple as I just explained it. There are very many factors which affect the uptake and the bioavailability of trace elements, and they are both biotic and abiotic factors. So it's not the same for every organism. Depends on the type of organism, especially on how they feed. Are they benthic feeders? Are they pelagic feeders, etc.? Also depending on age and size and gender, susceptibility for certain metals, the habitat, nutrition, uptake kinetics. These are all a number of the biotic parameters which may affect the bioavailability. And there are also abiotic parameters which we have more control and knowledge of, which is the metal speciation in the water quality parameters, and for the sediments, the sediment characteristics. Because if they're benthic feeders, it will depend on how the metals are bound in the sediments. And Yue will explain in the next presentation all about these sediment characteristics. So how do we assess this bioavailability? The most common approach is to look at the organisms and see what their uptake of these organisms is. So that's an body burden approach, ecotoxicological survey approach on the organisms in the environment that you're studying. Or you can calculate aquatic exposure to biota using computational models. These computational models will assess, depending on the speciation of your metals in solution, what the free ion concentration is in solution. And there are also models taking account this biotic ligand model, taking into account which ligand can be taken up by the biota. These are computational models which you can very easily assess, which are also even freeware. But you need to know the speciation in solutions. So they are based on thermodynamic equilibrium, which is not always the right case, as you will see immediately. So there are other experimental methods to analyze the speciation of the metals in solution, either ex situ in the lab or in situ. So these are techniques which rely on chemical speciation and selectivity of the metals. And which approach is better, the thermodynamic equilibrium model or the kinetic speciation model? Depends actually on how fast the metals can be taken up by the biota. If the metal uptake is slow, that means that the concentration of free metal ions in solution will remain relatively constant. Then your uptake in biota will be directly related to your concentration of free metal ions in solution. Then your free ion activity model or your biotic ligand model there apply. But you can have situations where the uptake is fast. That means that the concentration of the metals near the surface of the cell membrane will decrease, and you will have to have resupply from the solution to the interface with the organisms. And this resupply will actually depend on how metals, I can do it this way, how metals can be dissociated from the ligands into the free metal ions. So in bulk solution, we have both the free metal ions and the ligands. If the uptake is slow, then the concentration of the free metal ligands is the dominating factor. If the uptake is fast, the organisms will be taking up both the free metal ions and the fraction of the metal which can dissociate and be taken up by the organisms. So there will be a resupply of free metal ions due to this dissociation of the metal species. And this is where DGT is actually very interesting, because DGT does actually that. So as you have seen, how does a DGT device look like? There are 3 layers held in a holder with a back cover and the front cover. The layer in contact with the solution is first a filter, and then you have a diffusive gel layer, and at the back of that diffusive gel layer you will have a gel layer containing a resin which will bind your metals. And what will happen? Here is your solution containing your free metal ions and your ligands. They will diffuse into the diffusive gel. Also your metal ligands, which are small enough to diffuse into the gel, because the gel has a pore size of about 1 to 10 nanometers. So all inorganic ligands are small enough to diffuse into this gel membrane. When they reach the interface between the diffusive gel and the resin gel, they will be taken up immediately by the resin gel, because the resin gel contains a resin which has a very high affinity for the metals. So the uptake will be very fast on the resin layer. And then you will have a resupply of metals by the dissociation of the ligands into the free metal ions. And these metal ions will be also taken up by the resin. So DGT will measure everything which can dissociate during the time of diffusion from the solution until the resin layer. So DGT actually gives you a flux of permeant labile species through the gel. Everything which is too big, colloids, large colloids, will not be able to enter into the gel, but all the small ligands will be able to enter, and everything which is labile enough to dissociate and bind to the resin will be analyzed. So how do we use this technique? What will happen in the solution? You have a constant concentration of your metal in solution. When it diffuses through the gel, it will bind on the resin layer gel, and it will be taken up by the resin layer gel, so that the concentration at the interface of the diffusive gel and the resin layer gel will be 0. It will be 0 if the uptake is fast enough. So we have a constant concentration in solution. We have a concentration 0 at the interface with the resin layer. So we have a gradient. And when we have this concentration gradient, we will have a flux, a diffusive flux. And this diffusive flux can be calculated by the Fick's first law. And Fick's first law says that the diffusion flux will be equal to a diffusion coefficient, D, times the concentration gradient, and that's the difference in the concentration between the bulk solution and the resin gel layer. So it's C minus 0, which is C, divided by the thickness of the layer through which it has to diffuse. And this is this delta G, which we can determine because we make these resin layers ourselves. A flux is also per definition a mass per surface area and per time area. So if we combine these two formulas, we get the well-known DGT formula, where we can calculate the concentration of the labile species in solution, which is called the CDGT concentration. And this will be equal to the mass, and this is the mass of the metal accumulated on the resin gel, times the thickness of the diffusive gel, which we know, the diffusion coefficient divided by the diffusive coefficient, which we have determined in the lab, the time of deployment, T, which we also know, and the surface area, sorry, which is the surface area of our filter here, of the window. So we know all these parameters, so we can calculate the concentration sorry, of the labile species in solution. So there are many types of resins which are used depending on what you will bind, because DGT can be used for both organic and inorganic compounds, but now we're looking at trace elements specifically. And the most typical used resins are the Chelex 100, which is containing iminodeacetate functional groups. And these are very efficient to bind doubly and triple charged metals, such as the transition metals and the rare earth elements. So depending on the pH, different of these groups will be protonated or not. But at neutral pH, it will be essentially these carbonate groups, which are in their anionic form, so which will have an extra affinity for the metals as well. So you have also some other metals and also metalloids, which are present in solution as oxyanions, such as arsenate, antimonate, molybdate. I should have written them down, sorry. And for these resins, the Chelex is not very efficient. There we use other resins. Other resins, the ones which are most commonly used now, are the zirconium oxide resin, titanium oxide resin, which is called Metsorb. And now also another resin has been developed for that, and it's containing iron oxyhydroxide groups. This is Lewatit FO36. And there are a number of resins which also can be used for specific forms of the elements. So for mercury, for example, the resin containing sulfhydryl functional groups has a higher binding affinity than compared to the Chelex 100. So for mercury, we do not use Chelex 100, but we use this mercaptopropyl functionized silica gel. And this has sulfhydryl binding groups, and these sulfhydryl binding groups are also very efficient in binding arsenic 3. So we can measure specifically arsenic 3 using this MPSI resin. So what is a typical workflow? So we have we have deployed our piston in solution for a certain amount of time. We take it out of solution. We're going to elute the gel, the resin gel, and the Chelex gel is typically eluted in 1 molar nitric acid, and then we do the analysis typically by ICP-MS. So now I'm going to give another couple of examples of where these DGTs have been used and have been shown to be interesting for this bioavailability studies. So one of the older studies is already looking at cadmium and periphyton. It's a study of Braddock et al. In Environmental Science and Technology of 2009. And there they compared DGT labile fraction and also did calculation of the free cadmium concentrations with computational models and compared this to the uptake of cadmium in the periphyton. And it was very clear that you had a very good correlation between the uptake in the periphyton with the DGT labile concentrations and not with the free cadmium metal ion concentrations. So it means that the uptake was very fast and that this resupply of these labile ligands is necessary to explain your uptake in the periphyton. So in the next presentation, you will hear more about the use of DGT in sediments and soils, but one of the most commonly used aspects on the bioavailability is to look at the uptake in vegetables. So there you need to deploy your DGTs in the soils to see what can be taken up by the plants. And in your soils, you will also have the problem that your concentration at the interface of your device, your DGT device, and your and the concentration in the DGT device will not remain the same because you have a very small amount of solution in contact with the device and you're going to deplete it. You're going to remove your concentration of your labile metals from solution. So you're going to deplete the pore water from the labile metal fraction. So here, in order for the in order for the metals to be taken up by the DGT device, you will have to have some remobilization from your soil into the pore water that it can diffuse into this device. So this depends on your capacity of your soil and also on the resupply kinetics from the soil. So we can calculate R value, which gives you the concentration of your CDGT compared to your concentration in the soil solution, which is your initial concentration in the soil solution. And this gives you information on the resupply from the solid phase. And this will be also important for the uptake into the plants because they actually do the same. The uptake into the plant's root will also deplete the concentration at the interface of the soil and the plant. So the plants are removing metals from soils And the labile metal fraction in the soil will be determining in how much can be present in the soil solution and how much can be taken up by the plants. Assessing the labile fraction in the soil is often done by selective extractions, as you have heard already yesterday. And the exchangeable fraction is the most labile metal fraction. This is a fraction which can just be mobilized when your soil is in contact with a small concentration of electrolytes to have exchange, cation exchange with the solutions. Your concentration in soil solution can be determined by extracting the soil solution. Most commonly it's done using rhizons, or you can calculate the calculation of the free metal ions in solution with speciation models. Or you can apply a DGT, which is actually going to assess your soil solution and what can be liberated from your labile metal pool. So these are very commonly done experiments with this type of availability assessment. You're going to grow plants, and in the same solution, you're going to assess the soil solution with rhizons. As you see, these rhizons inserted into the pots. You let the plants grow. You can calculate the uptake in the roots, in the shoots, in the leaves of the plants. And then you can compare it with your DGT fractions. Oh, sorry, I didn't give the picture of the DGT. So you deploy a DGT in the same soils to assess the bioavailable fraction. And so this bioavailable fraction is the effective soil concentration, the CE, which is here. And then you see for the elements here, you have cadmium in beans, or zinc in lettuce, copper in onion, nickel in carrot. You have a very good correlation between the uptake in the beans and the DGT labile concentration. So it will not be the case for all plants, because as I said in the beginning, there are many biotic factors which also affect the uptake. But for the plants where these scenarios are the uptake scenarios, there you have a good correlation between your CDGT and the uptake in the plants themselves. So another study is a study of Tian et al. In 2008, where they looked also at the uptake in rice related to the uptake in soils. And here they also compared DGT concentrations with soil pore water concentrations, or doing different types of selective extractions to assess extractable and bioavailable fractions. And there also DGT gave overall the much better correlations between both the uptake in the roots and in the grains compared to the soil solution concentration, which only gave very good results for cadmium actually. And extraction procedures were actually only quite efficient to assess the zinc bioavailable fraction. So it depends both on the composition of your soils and the uptake mechanisms of the biota of the plants here to assess this bioavailability. And this has also often been applied in rice and arsenic, because arsenic in rice is in many areas a problem due to the high natural occurring concentrations of arsenic in some areas, and the ease of uptake in rice. And there's a paper of Williams et al. Who also made a mathematical model which can actually concentrate or predict the concentration which you will have in your rice, depending on both the concentration of arsenic DGT and the concentration of DOC in solution. So he made this model which can predict how much will be taken up by the rice, because there will be a competition between your arsenic bound to organic matter, which will be not taken up by the by the rice, and your labile fraction. So here also for the arsenic, we do not use Chelex, we use either Medsorb or zirconium oxide as a resin to evaluate this. So also another study which was done by Zhang et al., which looked at the uptake of nickel in radish in the shoots and roots. And also here, your DGT, these are in amended soils, so these are enriched soils enriched in nickel. You see a good uptake, uptake related to the DGT labile metal fraction. So that was a lot about plants, but it also is used for benthic invertebrates. And what is the problem with this benthic invertebrates? They will accumulate metals both from the overlying water and from the pore water. So it's really this interficial concentration which is important to be able to evaluate. And this is a paper of Stewart et al. Of 2012 in Environmental Science and Technology, where they used DGTs to calculate the flux of the available metal from the pore water into the device, so the flux which can be taken up by the pore waters, and related this to toxicity. So they used copypods, and they looked at the different sediment compositions, so either sandy sediment or silty sediment, very muddy sediment, to look at how these metals are released from the sediment and how this is related to the survival rate of the organisms. So these were also in spiked experiments where you spike your sediment with different concentrations and you look at their survival rate. And here you see that there was a very good correlation between the survival rate and the predicted DGT fluxes. So it can also, these fluxes can predict what will, in different sediment compositions, what concentrations will be released from the sediment, what can be taken up by the organisms, and then for very sensitive organisms, it will also give you an estimation of your survival rate of the organism. So it's a really good ecotoxicological tool here to assess the potential toxicity. Sorry, one more about uptake in fish. So that also has been used to look at the toxicity of elements in fish. And for example, aluminium is a toxic element, and especially in acidified ponds. Aluminium has been shown to be a cause of death of many fish, especially in nutrient soil, lakes with nutrient-poor soils, releasing these aluminium from the soil into the water. So here, what did they look at? They looked at the concentrations of aluminium, of course, in the gills of the fish. And they looked at the stress factors, and the stress factors, they looked at the concentration of glucose in the blood and chloride in the plasma. And there you also saw that the compared to the DGT uptake, there was a good correlation between the DGT measured aluminium concentrations in the soil and the uptake in the gills, and also related to these stress factors, which were the indication of the unhealthy conditions of the fish. And there are some other publications also which are trying to use this DGT to assess this metal toxicity in aquarium studies. And the last example I would like to give is one that we did in our lab ourselves. It was looking at the uranium bioavailability in function of the sediment composition. And the sediment composition that was used with either pure sand, quartz, or different clay minerals, kaolinite and smectite, iron oxyhydroxides, because the aim was to evaluate the toxicity and bioavailability of uranium in uranium mining sites, so where you have a lot of iron oxide deposits as well. And then a mixture of everything. If you mix the sand with the clays and iron oxide, you have a sediment which is well comparable to a real sediment. And these sediments were spiked at different concentrations of uranium in different beakers, which were made so that we could take time samples every 2 days from day 0 until day 10. And in these experiments, the sediments, the organisms which are introduced into the sediments were chironomids. These are larvae of mosquitoes. And they are very good indicators, very good accumulators, and very good indicators of metal pollution and availability. And they are very, very resistant also. So we didn't want them to die. We wanted them to accumulate so we could measure what was inside these organisms. So at the same time, also parallel experiments were done with DGT exposed in the same way, but without the organisms. So this is what these kind of beakers look like. So this is a sand experiment. It's just sand, and we put the organisms inside. The sand has been spiked with the uranium. The whole procedure I will not explain in detail. And then overlying water has been added, clean overlying water has been added, organisms added, and then they are incubated in a thermoregulated chamber which stays at constant temperature and which has a day-light sequence. Oh, this is how the little poor animal is swimming. So they usually live up to a couple of weeks before they turn into larvae. So these experiments are usually done at a certain phase of their larval stage. And of course, you may not wait too long. You don't want them to become flies. So after the exposure time, for the DGTs, you take out the DGTs, you remove pore water, you remove overlying water, take a sample of overlying water, take a sample of pore water with rhizons, remove the larvae, lyophilize the sediment, so actually analyze all the phases. And these chironomids, we rinse them with water, then with EDTA to actually remove what is adsorbed on the surface, and then they are placed in ethanol where, of course, they don't survive, and we can use them for analysis. So what kind of results do they give? We see that we have a very different accumulation in function of the sediment composition. We have, of course, an increase in the concentrations in these currents in function of time. And this is very different for the different types of sediments. The survival rate was very high in all the experiments, except in one of the experiments with one of the clay minerals, smectite, and it's not due to the uranium content, it's due to the high colloidal nature of this solution, which is not very good for the survival rate. So we can calculate our bioconcentration factors as the ratio of the concentration in the chironomids compared to the concentration in the dissolved phase. And then we saw that we had quite high bioconcentration factors in the solutions containing hydroxide feces and in the composite solutions. And if we compared the DGTs with the pore water, we saw that we had no correlation between DGTT and the pore water concentrations. That correlation was quite poor, but we look at the concentration in the DGT and compare this to the chironomids, then we had a good correlation for the different experiments between the concentrations accumulated in the DGTs and the concentrations accumulated in the chironomids. So it can give you a good indication of what can be taken up by these organisms. So this was the last example that I wanted to give. So just to summarize, DGT has a very solid scientific foundation and has very many applications also for the bioavailability. It's very important also, it measures an average concentration and also an average available concentration, because concentrations can change in function of time, and DGT integrates actually all these concentration changes. Also, when you have contact with solid and solution, it gives you the concentration at the interface of the solution. And it mimics biouptake. And it's also very interesting because it can be used as a multi-element tool at high resolution. And this can be used for both sediments and soils. And it's suitable for environmental monitoring, speciation, bioavailability, toxicity assessment, and also to study various biochemical processes. Okay, this was my presentation. Thank you very much.
Thank you very much, Professor Martin Leemakers, for a very interesting presentation. I think for all the audience, if you have questions, or we can have time for 2 or 3 questions now, but at the end we still have the discussion panel, so all the questions remaining we can raise on that time. So please, if you have any questions, just raise your hand or just simply unmute the microphone and ask Professor.
May I have a question, Martin?
Of course, of course.
Yes. I'm very interested in the methodology, DGT methodology that not only facilitate the process of sample preparation, but also increase the accuracy and also can separate different metal species, for example, organics and inorganic species of metal pollution. And my special interest is in the uranium. The paper, the thesis in 2018. Can you come back to the to that slide?
Yes, of course.
Yes, because one thing is we have some special place that we also have the uranium with high concentration in some mine in Vietnam.
Okay.
So we also assess the degree of concentration of radioactive elements in the area, for example, uranium and thorium.
Yeah.
My question is, can we also use this methodology for determining both uranium and thorium concentration in the soils and in the sediment, for example?
Yes, it is possible. Uranium is much easier to measure than thorium because thorium will be a much lower concentrations, I think.
Em bị cách ly, ta phải nhờ sinh viên cầm chìa khóa đến, anh cầm giúp em sẽ cho người ở bên chỗ phòng các phòng chỗ văn phòng xuống, chỗ nhân sự xuống họ lấy luôn.
I didn't understand that, but
thank you. I understand that. Yeah.
Yeah, it's
certainly possible to measure. Yes.
Yeah.
So that means we use the same DGT setup, and we measure both uranium and thorium.
Yes, I will have to check because we use different resins for uranium. We use a diphonics resin, which has a much higher affinity than the Chelex resin, and which you can use for longer periods of time.
Okay. Yes, I understand.
But I think it's also suitable for thorium. I will have to check, but it depends on the redox conditions of thorium. But I think it will also be suitable. But I will check that for you.
Okay, thank you very much, Martin.
Okay, so just one small questions from me, Martin. I'm also interested in the using DGT to to take the sample of persistent organic pollutants. You also have mentioned that in the talk. Do you have information that you or other groups has been using that DGT for examine the contamination of organic pollutants in soil or in water as well?
I think Yue can answer that because she's the one working on this type of pollutants also.
Definitely, I think DGT until now has been widely applied in polar persistent organic pollutants. Non-polar ones are more difficult because it's not easy to choose a suitable diffusive gel because the non-polar organic compounds will bond with diffusive gel. Then the principle of DGT will not exist. In our lab, together with my previous postdoc and PhD, we tested the DGT for endocrine disrupting compounds. Yet it has been published 2 or 3 papers. Then we are testing now the PAHs. So it's possible if you have, and I know it's working well for PFAS, for antibiotics, for pesticide, for almost all polar persistent organic compounds. You just need to find the suitable, as Martin proposed to Ding, if you want to test any new chemical compounds, you need to look for a suitable resin. But I think organics, it's much easier. Carbon-based resin are normally all working for organic pollutants.
Yes, so that's great because I really concerned. So in that case, we can move on with that kind of proposal in Vietnam as well because it's a very good technique to do it. And for example, it at one time we take the sample, then we can deploy the different kind of DGT to test the different type of pollutants in the same water bodies or in the same ecosystem.
To be honest, we have to admit, our laboratory, we don't have chemical instrument. We only, I think you were involved in one day, the training of Calyx. It's kind of bioassay screening technique. It will measure the group of, because like EDCs is a big group of chemical compounds. We measure the total, the group of these organic compounds. Individual concentration we cannot do, but in Vietnam, if you have a very good GC mass spectrometry, combining with DGT, I think you just need to build up your own methodology, then you can measure it without any problem.
Okay, thank you very much. That's very good. Yeah. Okay, so the time is up, so we have to move on with the second presentation today from Professor Yui Gao with the title DGT Application in Soils and Sediments. So Yui Gao, please, the floor is yours, Professor.
Can you see my presentation now?
Yes, we saw it.
Yeah, the full screen. Okay, so shortly, I will not introduce myself again. You all know me. So I will talk about understanding. It's a little bit more, it's advanced technique, advanced knowledge now. Not only the technique still the same. What we are going to do is to understand the biogeochemical processes of trace elements in marine sediments and also in soil at various spatial scales. It's actually the two PhD thesis of my PhD student, so I list their name there also. I will give the laser pointer. So there's two PhD work. So when we talk about the sediment, why we need to study sediment, actually yesterday already, I don't remember the name of the professor from Hanoi University of Science and Technology. I think Hong gave the explanation. The chemical pollutants, chemical compounds in the aquatic system, you will see often people will think they exist in the water column, but actually don't forget there is another compartment in the aquatic system. It's very important, is the sediment part. And sediment in the aquatic ecosystem behaves both as a sink and a source of contaminants. So chemical compounds can sink to the sediment temporarily, depending on the depth, buried in the sediment. You think is safe, but actually is not always all the time safe, because when the chemical physical parameters change in the sediment, those compounds has a big risk to release back to the overlying water. So it can be also a source of contaminants. And as you know, the massive substance exchange between water column and sediment happens every day, every minute, every second. And why is important of sediment? Because sediment are also the habitats for, you see, so many species of invertebrates and algae and bacteria. So it's also a key compartment for carbon cycling. You know, sediment bury a lot of carbon, organic matters. So it's very important compartment for carbon cycling and the bureau, as well as for trace element cycle. Because one redox condition changes, a lot of trace element can be absorbed to the sediment or released back from sediment to the water column. But every time when we mention sediment, people will think is the solid phase. because in your mind it's the mud, but actually inside the sediment there are two compartments also, pore water and sediment solid phase. Today I'm going to give you something mostly in the pore water, but we also did some solid phase treatment and analysis. But I would like to mention to you now, I will mention again for each study is pore water study and which one is the solid phase study. So it's different. And the common research on sediment means solid phase, but we focus not only solid phase, but also pore water, which is more difficult. Why the pore water study is more difficult? Because the available volume of pore water is small. Secondly, it's difficult to keep the original condition of the pore water because a lot of sediment are anoxic or suboxic condition. Then how you can keep the original condition of this pore water and let your sample become representative, it's quite difficult. You need to look for a method to keep the original condition of the pore water. Of course, you may work in the nitrogen protected atmosphere, but it's also not very easy. Another last difficulty is lower resolution of element of metal profile will be obtained by the classic pore water methodology. I will show you now. So what this study focus on, if we look at the structure of the sediment, this is the overlaying water and this is the border of overlaying water and the sediment. What happens inside the sediment related to trace element biogeochemical processes? We can see there are a lot of organic carrier phases. They may generate the dissolved trace metals. Then there will be exchange between water column and the sediment in the pore water. You see this is the pore water. The gray zone outside are the solid phase. Then of course there will be also the dissolution of those minerals like oxidative, acidic condition will make them dissolute, or they can do a kind of precipitation from pore water to the solid phase. You see this is also double directions. And also the iron manganese oxide reduction, oxidation, adsorption, all the time happening between the pore water and the solid phase. And again, the dissociation of the oxidative metal sulfide, for example, iron sulfide and other metal sulfide can be oxidated to be released to the pore water. Of course, then the pore water can be precipitated to the solid phase too. So we can see inside the sediment, there are a lot of dynamic processes happening all the time. So that's why it's so important to study those processes, to understand these processes, because there is so big potential. The dissolved trace element can be released back to the overlying water and to give the risk to the living organisms in the overlying water or even in the benthic area. Then, as I said, classic pore water profile. How to get the pore water profile of trace element? We normally do a kind of slicing of the sediment core in nitrogen protected atmosphere. Then afterwards, by centrifugation, to get the pore water for each 2 or minimum 1 centimeter, and to analyze the pore water sample to get the metal concentration. So I gave an example of cobalt here. So this is the pore water profile of cobalt obtained by centrifugation. Then you see every 2 centimeter we have a data point. Then we produce such kind of profile. It's pore water profile of cobalt obtained by classic centrifugation technique. And secondly, when we look at, I will not repeat about too much DGT, but later I'll explain a little bit the principle DGT works in sediment. But now I start to show you the idea why my PhD student wanted to do such kind of study. If we look at the pore water profile of cobalt obtained by the DGT, we see much more data points and shows much higher resolution of the profile. And we can see there is a good correlation for some depths, like -5, the remobilization of cobalt obtained by centrifugation coupled very well with the DGT technique. But if we look at the other depths, the centrifugation could miss some important information. For example, here at the depth -1, there is also a small mobilization, but will not be observed by the pore water because you averaged the depths of the profile. So some important information could be, averaged or missed by the traditional sampling methodology. For example, here also, you don't observe anything here. And yeah, something still good correlated with it. But if we see the general trend, they normally have a good correlation between the pore water profile and the DGT profile. And we ask ourselves also, are we really satisfied already with this resolution? Is every 0.5 centimeter we have one data point. Here is every 2 centimeter. So it could be much more higher resolution, but higher resolution will give what kind of information? Don't forget, sediment is different from water column. If we consider water column as a type of a homogeneous system, then sediment is completely heterogeneous system. So it's different from water. Then now we are only able to look at the vertical distribution of cobalt, but how about the horizontal one? Because it's a heterogeneous system. So horizontally, cobalt will distribute also differently in the horizontal distance. But with this 1D profile, we cannot see horizontal distribution of cobalt. Here, this is the concentration. This is not horizontal distance. This is the concentration range. So it's really necessary we also look at both vertical and horizontal two-dimensional profile of trace element or not. So the following study can answer your question. We choose a few study areas and to compare and to see a different application of this technique. So the two study area is the North Sea, very close to Belgium. Belgium is somewhere more or less here, I think. Martin, am I right? Here is Belgium? I think so. Then we are very narrow connections. We choose several study areas in the Baltic Sea. I'll explain why we choose the Baltic Sea. It's completely geochemical conditions than the North Sea, and you will see it give you completely different type of result. And where did we work? Of course, we choose somewhere close to the Belgium coastal area. You see the Belgium part of the North Sea, and mainly we work a lot along the coastal side, because coastal side is the heavy contaminated side by the harbors, by the transport, by some anthropogenic activities, because there are few nearby industrial area close to the coastal side of Belgium. And the North Sea, we choose somewhere Gotland Basin, close these two basins of two sampling stations in the west Gotland Basin and in the eastern of Gotland Basin. So here I first talk about the Belgium coastal zone in the south of the North Sea. And we can see the water depth of the North Sea close to Belgian part is around 50 meters. And the bottom water is fully oxygenated. It's very important you know such kind of information because it will influence the biogeochemical process of trace elements. And the sediments, the type of sediment is clay to sand. And I have to tell you, with sandy sediment, it's very difficult to use DGT technique to measure the pore water. But even with the classic methodology, it's also not easy to work with sandy sediment because the pore water will be difficult to be maintained in the core. Then the Gotland Basin, if we look at here, the water depth is 50 and bottom water fully oxygenated and sediments clay to sand. But if we look at Gotland Basin, actually while we look at there, Gotland Basin was a seal, almost a completely sealed system. So what does that mean? Almost without any input of the fresh, the water from other source, with very small part from the North Sea. Then what is resulted in the Gotland Basin, you see the development from the beginning of 19th to 20th century, the very heavy development of hypoxia over the time of this Gotland Basin. Now, if you look at the beginning of 19th century, the right area represents the scale of the hypoxia. So you can see the beginning of 19th century is just some spots, then gradually developed bigger until now, much bigger area, almost the whole basin. In each summer, there is hypoxia happening, means there is no oxygen available even in the water column. So the water depth is normally bigger than 100 meters, and the bottom water is long-term hypoxia without oxygen, and the sediment is mostly clay, and it's ideal for the application of the DGT technique. Then the research objectives of this study is to investigate mobilization processes of trace element in marine sediments with contrasting conditions due to oxic and anoxic overlaying water at various spatial scale, large scale, fine scale, and two-dimensional high resolution also. And the main goal is to expand our knowledge on early genetic processes that were previously investigated at coarse resolution, at the larger scale. And the detailed objectives are as follows. Yeah, of course, to reveal mobilization mechanisms at fan scale that might have been long time overlooked at larger scale. And by comparing the result obtained from different methods, DGT and the conventional sediment slicing is the same as what I mentioned. Slicing or centrifugation is just a similar technique. And processing the result with modeling, we aim to have a holistic understanding of trace element exchange between sediment solid phase and pore water. So we want to understand the mechanism between the exchange between sediment solid phase and pore water. What is there? Is release, removal pathways, or the resupply kinetics. And also to review horizontal gradients of trace element mobilization in pore water. So this is another dimension. If you see, I gave the example of vertical. We want to look at horizontal gradients of trace element mobilization, and also we want to get insight into trace element micro-niches. Micro-niches is a small aggregation of organic matters inside the sediment, full of micro-niches inside the sediment, how the micro-niches formed, how they appeared, and what is the mobilization and immobilization mechanisms inside the micro-niches. So as Martin has already introduced the principle of the DGT, and you often see this shape of DGT sampler. It is a common one applied in water column. But inside the sediment, we have another type of sampler. You see it look like this. But the principle is the same. It maintains also 3 same layers of membrane, so the filter membrane, diffusive gel, and the resin gel. And the length you can see of the probe, we call it sediment, DGT sediment probe, is about 240 millimeter, but the surface area you can see is 150 millimeter multiplied by 18 millimeter. So the length is 150 and the width is 18 millimeter. So it's how it look like, but the principle, the basic principle is the same. When we talk about the technique, the DGT technique, I think I wouldn't spend too much time on this equation again. It's a common equation we normally use, but I want to mention what is the difference of when we apply DGT technique in sediment than applying it in the water column. So we can see actually, as Martin also shortly introduced, the kinetics inside the soil is the same, and the sediment is different from water column. So if it's in the water column, the condition will be like this. So the linear concentration gradient will be built up very quickly within 20 minutes to half an hour when you deploy the DGT pistons in the water column. So you always get, we think, in a good water flow condition, you may always get enough supply of the target element you want to measure. So it's fully resupplied case, but inside the soil and the sediment, it can be different. Normally, such kind of case almost you will not see. But often the other 2 cases are happening inside the sediment. What happening there? When you deploy DGT inside the sediment, the first available source of trace element will be from pore water. You know, this black dots present the solid phase, but this white spaces means pore water. So the pore water concentration will be the first choice for the DGT to bond with. Very quickly, or take a bit time, the concentration of the pore water of trace element will become depleted. Then there should be a mechanism, should be or not, we don't know. We need to study the type of the sediment. There will be a resupply from sediment solid phase to the pore water. How fast, how slow, we need to understand by a kind of model, but I will not go to very details about this. It's too complicated for you nowadays. We are able, by using that model, we are able to understand how quickly we can get resupply from the solid phase to the pore water, or how slow, or even without any resupply from solid phase to the pore water. Then the case is like that. It's pure diffusion. Everything finished in the pore water, then finished. There is no resupply from solid phase to the pore water. So that means there are 3 cases inside the sediment. So we call fully sustained case. Then in that case, we need to calculate the R value. What does that mean? R value means the DGT measured concentration divided by the pore water concentration. That's why when you want to understand the mechanisms, the releasing, the sorption from solid phase to the liquid, we need always carry out the DGT in the parallel way. We should measure the pore water concentration. So if the R value between 0.9 and 1, this is continuously resupply from the solid sediment phase to pore water to sustain the initial bulk concentration of trace element. But actually, as I said, this is very occasionally happening case. Mostly are the other two cases. The second case is partially sustained case. R value should be between 0.9 and I think this is the R value, value obtained from the model. So there is a partially resupply from the solid phase, but insufficient to sustain the initial bulk concentration of the pore water and to satisfy fully the DGT demand. So it's only partially. But as I said, there is an extreme case, only diffusion case. So there is no resupply from the solid sediment phase, and the supply of solute to the DGT is solely by diffusion from the pore water. But how to get the knowledge about which case of sediment do you have? You may deploy different techniques of the diffusive gel. Then you may measure which case of the sediment you are facing to. So it's not so complicated to know. You just do a little bit more test. You will know it's A case or B case or C case. But sometimes maybe it's not very useful for you if you don't apply a model for such kind of study. That's why in our small project, we only apply normal techniques of diffusive gel. We only want to know the DGT measured concentration between the sediment and the DGT probe. So the RDIF can be obtained by DIF's model, and usually the value is around 0.1. So if R between 0.1 and 0.9 is partially sustained case, if R smaller than 0.1 is a diffusion only case. And I also like to show you a little bit the sampler, the sediment sampling tools we used in these two studies. In the Belgica, I think we use the Reineck box course. And in another cruise, I think this is equipped by the Norwegian boat, if I understand well. So it's another multi-core system, but all these devices are helping you to get the proper sediment cores. So what we want to get. So we normally get sediment cores like that. So this is the sediment. You keep in mind for such kind of study, you always need to keep a little bit overlying water because it's important to help you to protect the sediment and to let you know what is the activities between the overlying water and the sediment solid. So we took normally one core for pH. EH means redox potential measurement because these two parameters are very important parameters influencing the mobilization of trace element in sediment. So all the time we measure pH and EH in the sediment core. Then to carry out the traditional sediment slicing and centrifugation technique, we work on the boat. We need such kind of glove bag. You can see this look like you can stretch your hands inside and to work a little bit. And nitrogen gas protected atmosphere. So here you see the tube can be connected to the nitrogen bottle. So you work under the oxygen-free condition. Why we need to work on the oxygen-free condition? Because a lot of sediment are normally anoxic or suboxic condition. So the trace element, they present as their original form. For example, iron 2, if it's in reduced form, it's iron 2. But if we didn't work in proper way, we may exposure the sediment core to the air and iron 2 plus will be oxidized to iron 3 plus. So you will not be able to measure the representative element as you want to measure, like manganese 2 can be oxidized to manganese 4, and all the other are the same. But as I said, the sediment core slicing, pore water, and solid phase collection, we get larger scale data. It's around 2 centimeter. Yeah? And the third sediment core, we are going to deploy the DGT. Then we get the Fender scale of 0.5 centimeter. Or if we apply the 2-dimensional high resolution analysis, we may get much finer scale around 100 micrometer for 2-dimensional measurement. So this is the classic pathways how the DGT probe will be analyzed. So after the deployment, you take the probe out from the sediment. The traditional way, you slice the sediment for every 0.2 centimeter strips. Then for each strip, you put it in the vessels and to be eluted by 1 molar nitric acid, as Martin already mentioned, for most trace elements. Then after a certain type of dilution, proper time of dilution, we do the analysis by ICP-MS. Of course, if you want to analyze 2-dimensional results of the gel, then you need to follow another pathways. So the instrument plays the key role for such type of analysis. Instead of using traditional SCP-MS, we connected laser ablation to SCP-MS. So laser ablation can work on the dry gel. So after the DGT deployment, we stop this process. We take the whole gel out. We will dry the gel. Then we mount the gel to the laser ablation cell, the sampling boat, you can say also, and laser beam will go through each depth. Then you can choose the resolution you want to achieve. And minimum, we can do 100 micrometer. Of course, you can choose 300 micrometer or 500 micrometer, but it will take a lot of time to do such kind of analysis. But it will give you much finer resolution of image of trace element. And another actually is kind of colorimetric methodology we can use. Normally, another type of DGT is called silver iodide DGT. And the silver iodide DGT is applied for dissolved sulfide. So as I said, if you want to analyze any new chemical compounds, you need to look for suitable resin gel. So for dissolved sulfide, we need silver iodide resin gel, because when silver iodide meet with dissolved sulfide, the chemical reaction will produce silver sulfide. And the gel itself, original gel, is a pale color. It's a bit like white color. But when it meets with dissolved sulfide, the color will change to brown. And it will produce different density of this brown color. Then by using the scanner, very classic scanner, scan the darkness of this silver iodide gel, then to produce a grayscale image of this is the final result. But the grayscale, then by using certain type of software, normally I think my student used the ImageJ, and to produce the concentration of dissolved sulfide. Of course, before that, you need to set up a calibration of the dissolved sulfide. This is the calibration of dissolved sulfide. We made it in our laboratory. Then by calculation based on the calibration curve, we may get the 2-dimensional high resolution image of the dissolved sulfide. You can see vertical dimension and horizontal dimension distribution of dissolved sulfide. But I'll explain this result later soon in details. And so I already presented you the methodology we use in these 2 studies. And the study area we carried out, first we want to see fine scale measurement, review 2 mobilization mechanisms using 1D, dimensional with vertical profiles. In Belgium coastal zone, we choose 2 stations, W1 close to Zeebrugge Harbor and W2 close to Ostend. I think all Belgium alumni, you know these 2 cities, the harbors there. And what did we do? So we measured the EH, the redox potential profile, and the pH profile. We see the pH of W1 varies between 7 to 7.6, lower than the pH of W2. So W2 is between 7.3 to 7.7 around. And the redox potential, the anoxic situation of W1 is more obvious than W2. But actually, after 2 centimeters below the sediments, both sediments in 2 stations become anoxic. So there is no oxygen available, anoxic situation. Then we observed 2 different patterns of the trace element. As we said, Martin explained, there are trace cation element, like we say copper, lead, nickel, copper, zinc, cadmium, cobalt, but there are also oxy ions. It's trace oxy ions like phosphorus, vanadium, arsenic. Then what we observe from the profile of iron, phosphorus, vanadium, arsenic, we see in the suboxic zone, the layer here, the blue zone here, phosphorus, vanadium, and arsenic were co-released with iron. We observe a remobilization of iron between 0 to -6 centimeters. Then we see also a correlated remobilization of phosphorus, vanadium, and arsenic in the same zone. But the trace cation element, if we look at iron, cobalt, lead, nickel, copper, we don't see a very good correlation between them with iron. We don't see cobalt, lead, nickel, copper remobilization correlated with iron at the suboxic layer, but there is a good correlation in the anoxic layer. So in anoxic layer, cobalt, lead, nickel, copper were co-released with dissolved iron and sulfide. And those results were already published in Environmental International in 2020. Quite proud of this paper because it's a high impacted journal, means the level of the study is quite good. And this is station W1. And if we look at station W2, that's the same. So the suboxic layer, trace oxy ions were co-released with iron, and in the anoxic layer, the other trace element released correlated with iron in the anoxic layer. Then he also calculated the correlation between oxy ions and iron in the blue if you remember blue, he called the blue zone, suboxic layer at station W1 and W2. Indeed, this relatively better correlation in the suboxic layer. Then we look at the anoxic layer, the correlation between trace metals and iron in the gray anoxic layer are even much better if you look at the R values. So at station W1 and W2. Yeah, he tried to apply different methodology to approve his result. Then not finish about Belgium coastal area, but finish this result. We go to the Gotland Basin to understand phosphorus and manganese mobilization. So as I explained to you, in the middle of the basin, the sampling site are chosen in the middle of the basin and have water depths from 120 meter to 240 meter even. It's very deep sea marine stations, and the bottom water is anoxic. So here is are the dissolved oxygen concentration profiles in the water column. So here the dark gray zone represent the sediment, and the blue is the water column. We see the concentration of oxygen decrease after about 60 meter depths in the water column, and the oxygen concentration suddenly decreased a lot until the bottom of this water column and the beginning of the sediment is totally anoxic. If you see this, the full sampling size, station 8, 6, 14, and 16, completely anoxic. And did he study? Yeah, he summarized his result. Actually, beside phosphorus and manganese, he also got other trace element profiles, but he found something interesting. So he focused on what he found interested part. So what he found, if we look at the large scale pore water concentration, we see a very good correlation of phosphorus profile and manganese profile. We in station 8, and also good correlation of DGT phosphorus profile and DGT manganese profile in station 8. This is also the case in station 6. But if we look at station 14, the pore water concentration of phosphorus had a good correlation with pore water concentration of manganese. But if we look at the pore water concentration of phosphorus, we see the decreasing trend. Is all the time decrease from the surface water to the increasing trend. From the interface of sediment water and to the sediment bottom, phosphorus concentration increases. But if we look at the manganese DGT profile, it's quite stabilized profile. There is no obvious increasing as observed in other two stations. So you want to know what happened here. If you see, I explained the correlation. If you see the correlation between other stations by look at the pore water concentration, they always have very good correlation, though all above 0.70, the R value. I mean, phosphorus and manganese. But if we look at DGT profiles, the phosphorus profile doesn't have very good correlation with DGT manganese profile in station 14, because the R value is only around 0.2. So you want to study the mechanism. What do you think? You think, as I explained, there is always an interaction between the pore water and the sediment solid phase. There is always some exchange between the pore water and the solid phase. So he got the pore water concentration. He got the DGT concentration. It means the label concentration of phosphorus and manganese inside the sediment pore water. And what else he can consider? So he thinks probably the source of solid phase to pore water having different mechanisms in this station. So he did the sequential extraction of the sediment, as I introduced you yesterday, and Martin also mentioned slightly today. When you deal with solid phase sediment, beside the total digestion, we may do the sequential extraction. We want to look at different fractionation of phosphorus from this solid sediment phase. So what he applied, this protocol you can get from the literature easily. So he applied the sequential extraction by using different chemical reagents to extract out of phosphorus exist in different forms. So first, he may get exchangeable, but secondly, he may get easily reducible and reactive iron bound phosphor is also called CDB bound phosphor because he used the CDB solution, is saturated dithionite bicarbonate solution. And thirdly, by using these two different chemical reagent, he may get autogenic phosphor phases and the other two phases. I highlighted these two because it shows the different result of station between three different stations. So if we look at the sequential instruction result for station 8 and station 6, what is the main existing phosphor source inside this solid sediment phase is CDB bound phosphors, means it's iron, mainly iron bound phosphor. Inside this solid source is closely associated with manganese carbonate oxide. But in station 14 is another source. It's not the CDB bound phosphor, but it's autogenic bound phosphor, mainly calcium bound phosphor. It's closely associated with manganese carbonate oxide minerals. So he found different mechanisms to explain why he got different result of the DGT for phosphor and manganese in station 40. So this is again a type of explanation. He found he summarized there are two scenarios in the Gotland Basin considering the correlation of phosphor and manganese in sediment pore water. If we apply the DGT technique, so you see it's differently as I explained to you in station 8 and 6. They have good correlation between the DGT profile and the pore water profile, and apparently it mostly linked to the CDB bound phosphor. Is also iron bound phosphor correlated to manganese carbon manganese carbonate phases. But in station 14 there is another scenario. Second scenario is DGT profile looks differently from DGT profile for manganese, but it's also different from the pore water profile. Shows the calcium bound phosphor is the main source to release phosphor to be measured by the DGT. So it's two different scenarios. So we can see like that. Above, I show all, if you see here, I show all one vertical dimensional profiles. So what information you can extract from such kind of profiles. Now we come to, do we need the two-dimensional images of those trace elements in the sediment sediment pore water? And we did two studies. One is in the marine station 130 in Belgium coastal side. It's not so far from Ostend harbor. I think it's 10 kilometers far from the harbor. And again, we did also 2D dimensional measurement of trace elements from the DGT probes deployed in those 4 stations in the Gotland Basin. So yeah, those results were published last year in Environmental Science and Technology. We are also proud of this study because it's the top journal in this environmental field. So those are the two-dimensional profile image. We don't call it profiles anymore. We call it image because you can see this is like a picture. It's an image for trace element and for also iron, manganese, cobalt. Sometimes we call them oxygen sensitive element, and those cadmium, copper, lead, also nickel, zinc. We normally call them trace metals. And we want to see those oxygen sensitive elements, do they have good correlation with the dissolved sulfide distribution? Because normally we know when dissolved sulfide concentration are high, we shouldn't observe high concentration of trace element because they will precipitate with dissolved sulfide to produce like iron sulfide minerals, solid phase. So the DGT shouldn't measure that phase. But if we look at the two-dimensional profile, what we observe here, he made simple comparison between the two-dimensional profile images result with the one vertical profile data. I think, yeah. So the right dot line presents the 1D distribution of trace element in the sediment pore water, and the blue, the black, very dense dots lines represent the average of the two-dimensional result. He averaged all the data to produce, but you can see the one-dimensional profile differs from the average of two-dimensional profile also. You see cadmium, copper, lead, iron, manganese, cobalt. So actually, from here, we already realize the two-dimensional image of element produce maybe a little bit different information than the 1D profiles of trace elements. But we look at into the details. Yeah, we can still say the general trends, they correlate very well. It's increase from interface to the deeper pore water layers. Then the oxygen sensitive element start to increase from the surface to the deeper sediment layers. They have relatively good correlation of the trends. So he summarized 1D profiles and 2D images are vertically well replicated, and the horizontal gradients are revealed by two-dimensional high resolution image. Because if we look at these three elements, the distribution of this element in horizontal way, we can see the higher iron concentration was mostly observed on the left side of the DGT probe. And manganese has even distribution horizontally on the whole probe. But the cobalt, if we look at the higher concentration were observed on the right side of the DGT probe. So we want to know what's happening here. We see actually cobalt remobilization on the right side mainly caused by the remobilization of manganese, but not by iron, because here the iron concentration is very low, but cobalt concentration are very high. But if we look at cobalt and manganese, they have good correlation on the right side. And if from 1D profile, sorry, I come back. If you see, okay, we can summarize the right dot line. Three element has very good correlation. We cannot say cobalt doesn't correlate very well with iron, but with manganese. We cannot say that because 1D profiles, they all look similar. But from 2D vertical distribution, you see the differences. Then, yeah. He also did the average all the concentrations in the horizontal way. Then he also in this figure, we also found the good correlation of manganese with cobalt, but not with the iron. And in the Gotland Basin, if you remember this hypoxia area, coincident peaks of copper and nickel was frequently observed in the Gotland Basin. If we look at here, nickel, copper has sometimes very good correlation at certain depths. If you look at station 8, it's mainly happened at -2 and not exactly here, but at station 6, we observe nickel from 1D profile. We observe a correlation between nickel and copper at depth -6, at depth -11 also, and see station 14 also a few simultaneous remobilization was found. So we did a kind of, we want to know why it's vertically we observe this coincident peaks, or horizontally what we will observe. So in the deepest layer of one station, we use the laser ablation SBMS to scan the dry gel. So we found the copper nickel. You see this coincidence remobilization of these two trace elements related to the remobilization of iron and manganese in the same area. So we can see such kind of, so he made this figure again to average the concentration in this small scale. Actually, this small scale, we also call it micro niches. If you remember, I introduced at the beginning, we want to study how this micro niches formed. So he averaged the concentration of this small micro niche of different element, copper, nickel, to see the correlation with iron and manganese. We see a good correlation between these 4 elements. So co-released from dissolution of manganese, iron manganese oxide, all can be co-released from dissolution of iron sulfide. All can be co-released from the degradation of organic matter. There are 3 possible mobilization mechanisms here. So to summarize, we feel is improved understanding with the decrease of the spatial scale. So from centimeter scale to millimeter scale to micrometer scale. And what we understand, the fan scale mobilization mechanisms were revealed if we only use the coarse and a little bit higher resolution. You won't see this fine scale mobilization, and the DGT concentration measured at fine scale is complementary to the total dissolved concentration measured at larger spatial scale. And the coincident mobilization of trace element as sub-millimeter, means micrometer spatial scale, inside the micro niches can be revealed by increasing the spatial scale. Horizontal distribution can be found by using high resolution 2-dimensional measurement. We can also see a little bit the chemical speciation to discuss this chemical speciation. He also summarized perspectives and the future plan. I don't know, it's interesting. Hong, do I still have time? I'm short of time now. Maybe I skip that. I will talk a little bit of the soil deployment. So the 2 parts I include in this presentation is soil sampling in the agriculture area in Flanders. If you were yesterday here, I show you the project we got to investigate the reuse of water treatment effluent to do the irrigation in the surrounding agriculture soil. Here is the wastewater treatment plant. So what do we need to do? We want to study the metal concentration background value in the nearby agriculture soil. So in agriculture soil, we use different parameters. First, the enrichment factor in metals is the indicator to assess the presence and intensity of anthropogenic contaminant deposition in surface soil. I think most people understand this simple enrichment factor. How to calculate it is when you have a sample, soil sample, you measure the metal concentration in the soil sample by using total digestion, then compared to the reference element. Normally you may choose aluminum, or you choose other stabilized element. For example, somebody choose iron in soil. So you may get then divided by the metal in the background value in the earth crust. So EF is bigger than 0.5, smaller than 1.5, suggests that the trace metal concentration may come entirely from natural weathering processes. When the EF bigger than 1.5 indicates that significant portion of the trace metals was delivered from non-crystal materials. So these trace metals are delivered by other sources, can be pollutants. But someone will find in different literature, they use different standards. Sometimes below 2, sometimes below 3, I believe. So what did we do? At the beginning, we did the annual investigation on the soil. So we just take some soil from the depths around 20 to 30 centimeter. We come back to the laboratory. We did the total digestion. So we have those results for each month. You see cadmium, lead, chromium, cobalt, nickel, copper, arsenic, and zinc. Then we observe the seasonal variation of these trace metals in different months, probably due to the cultivation of the plant and due to the application of natural fertilization by the local farmers. We indeed observe a little bit difference, different concentration for different months. For example, cadmium showed high concentration in November, December, February, and May, June also, but March, April is much lower. Probably they say during the winter time, the farmers start to use the natural fertilizer, you know, to nutrient the soil to prepare the next year cultivation. Then we know such kind of soil normally used for cultivate different crops. For example, maize, or they will cultivate plants and vegetables. So we consider the most deeply planted crop, maize. It's normally the root of maize can go to the depths of 60 to 70 centimeters. So we took every 10 centimeter soil sample. Then we go back to the laboratory. We analyze the depth profile of this trace element along the whole soil depths. So we see also different type of distribution of the trace element in the soil in March and also in June. I just want to show you. Then we see around 35 centimeters, there is mobilization of trace element for almost every element in the same type of the soil. We don't know why. We need to do the further investigation because this is the beginning. You see the result from June this year. And after that, the PhD student worked on this project. She also did the sequential extraction by using different chemical reagent. You get different fractionation of trace element. Then I have already showed yesterday this table. She applied that. Then we got different fractionation of different elements for a different types profile. You see iron, the exchangeable, the easier extracted fractions is here, is presented in different, I think it's different locations to have different distribution. And the right one is the exchangeable, here, sorry, is the exchangeable fractions for different elements. I made the mistake, I suddenly confused. And the second horizontal profiles shows the reducible fractions for the different element, then the oxidable fractions and residue fraction. Then she summarized in this kind of column figure. Then we see cadmium. Most of cadmium present as exchangeable fractions, so they are more mobile, labile. They should be easier measured by the DGT technique. But for example, lead and mainly exist in the reducible fractions could be partially measured by the DGT technique, but we are not very sure about it. But if we look at iron, mainly in reducible phases and also in the residue. If it's in the residue, means it's very difficult to be released from the soil. Then she carried out the DGT application in the soil sample. So here are the whole protocol, how she moistured the soil, how she applied the DGT on top of the soil. But those information you can find from any literature who use DGT for soil application. I will not go very details. And the results showed here the pore water, soil pore water concentration for each element. Here is the DGT concentration for each element. We see obviously the DGT measured concentration for each element are much lower than the pore water concentration because DGT measured the labile fractions of this trace element in the soil, and that's in different months. You see in the same station in different months. But what is the purpose to do this? The idea, we are going to use the DIFFS model, as I already mentioned in the sediment study. Also, we want to study how quickly, how slowly the soil solid phase release those trace elements to the soil pore water, then become bioavailable for the crops planted in the soil. So the next step will be plant the vegetables in such type of soil, try to build up the relationship between the DGT result or to see the pore water result, which one has the good correlation with the plant harvest parts, the trace element concentration in the vegetable part. So I think I finished my presentation. It's very long. Thank you for your attention. Here is a nice photo. Martin went with all these PhD students and colleagues from other organizations to the North Sea, I think. Besides the work, we have a lot of pleasure time. We went to the DGT conference in Vienna 2 years ago. So we hope we will meet you shortly in Vietnam. Okay, thank you very much.
Thank you very much, Professor Yu Gao.
I think I go beyond the time.
Yeah, but no problem because it's very interesting. It's long but very interesting and informative presentation, and I myself I learned a lot from that. And maybe just we have 10 minutes break for coffee, but during that's the time, if anyone have a question for Professor Yu Gao, please ask her directly and we can discuss together here.
Yeah, if you have any questions, feel free, because I want quite quickly. Those are the advanced studies. I don't know it's very clear for you or not, and feel free to ask. Okay.
It's
any type of question, because it's a quite complicated application. If you have simple questions, you may also ask.
Yeah, so I just want to discuss with you a little bit about I mean, when we take the sample from the sediment, the pore water concentration is very important, but also the mobilization of the metals from the solid phase to the dissolved phase is also very important, because it's according to the to our study, that it's very important to predict. For example, if we have the concentration in the sediment, then we also have the concentration of heavy metals in the water columns. But then with that concentration in the sediment, we want to predict that how to say the rate of release of the metals from the sediment to the water column when the condition is changed, and it's also potentially toxic to the organism, aquatic organisms. So
I will show you a very simple prediction, but we didn't do very detailed study. But according to the profile, I show you like very. It's not obvious here. Let me see if I have other.
Yeah, and you have mentioned that in
here. I show you here. If you look at the trace element, cadmium copper lead, the concentration in overlying water is much higher than in sediment. Yes, so it means big potential, those concentration will sink, all this element will sink to the sediment because of the concentration higher there. But if we look at iron, manganese, cobalt, the concentration in sediment part are much higher than water column. Of course, then there is a big potential. Those elements will release back to the water column based just simply on the concentration gradient. But if you really want to know the exact dynamic of the mechanism for such kind of sinking or release, we need to do more detailed study. We need to do, for example, a kind of Martin did it while I was doing my PhD together with her. We measured the benthic flux is from the sediment to the water column or from the water column to the sediment. But it's quite difficult to do in the laboratory condition at that moment. But there is a way to do it.
Yeah,
and in our small project, due to the condition you have there, we didn't include the pore water extraction because you need to have a nitrogen gas bottle, you need to have a glove bag, but you also need to have a staff has been trained already quite well. Maybe, I think Lian, if Lian goes back, I think Lian can help because she joined to do some, maybe, I'm not very sure. I'm a little bit confused.
We did do some pore water in one of the ponds because we used rhizomes and we did it directly.
Oh, yeah. I'm always thinking about.
It's possible to calculate diffuser fluxes from.
Then you can calculate easily. The rhizome, Martin brought to. This time, no, we didn't prepare for that.
No, but indeed, in the next
too complicated. It's too complicated for home when you are alone there,
If Tao goes back, then she can also do some extra work on this type of.
Great.
More complicated.
Yes. Yeah. Because sometimes the people just argue that the different trace element after sinking to the bottom of the ecosystem, then it stays there and it's not the releasing back to the water column is low, and it's not very dangerous for the aquatic animals, so something like that. But then we need to have the kind of hard evidence to show them that it's very.
Even the sediment which has sunk, it can be resuspended and transported further.
Yeah. Right.
That we see from the data that we have.
Yesterday you got the question about cadmium in different months, and you have high concentration of cadmium in water column. Why? Probably there is resuspension of sediment of cadmium to the water column in different amounts due to different condition. So it's possible. Yeah. No questions.
So all of you, if you have any questions or if anything is not clear for you, so please raise your hand and ask.
I think Tao later, after the New Year holiday, she should carry the DGT deployment in her soil sample she bring. I don't know, she was in, yeah, don't need a lot of sample, should enough.
Actually, I plan to go to the field as soon as possible to take the soil and post it to Belgium for her to do the experiment. But
yeah, we can ask Kwan to join because he will anyway do his master, so he can also join. Yeah. Okay.
Okay, so you and Martin, so a lot of people are very interested in your presentation. So after this workshop,
my part, I have no big problem, but the soil deployment, I will delete it because it's non-unpublished data. But for Martin, I don't know. But like presentation yesterday, no problem at all. I think Martin, I don't know what is the contents of her presentation. If there is no unpublished data, we don't mind to share, no problem.
Okay.
Oh, there are unpublished data, but I don't mind the sharing.
Yeah. Okay.
Yeah.
Yeah.
Today I invite Professor Chen Mingtian. He is the General Director of the Institute for Soil Chemistry and Fertilizer. But because of his time too tight, so he left already. But I think that the application of DGT in soil sampling, I think that is open up a huge application in soil chemistry in Vietnam, and I work with him in order to promote the DGT application in soil chemistry, and maybe next time I take the presentation to his institute and then represent to his staff also, and I think that is also very good opportunity to promote the methodology. Thank you.
Yeah.
And you, in one of your slides, it's very interesting for me that I saw the cadmium concentration in the topsoil is very low. So in the first 30 centimeters, something like that. In the picture, you show that. So,
yeah, is this one?
No, not that one. Maybe
this one. Actually, if you look at cadmium, because it's a trace element, and normally the concentration should be very low. But if you look at the soil here, yeah, the cadmium concentration you see higher than the other trace elements.
But
if I'm right,
look at the vertical profile. So
the vertical profile also. Here you see the centimeter here, 30 to 40. Yeah.
So that means, I mean, in the top layer of the soil, the concentration is very low. So it seemed to be safe for the vegetable crop because we grow the vegetable in the very shallow layers of the soil.
Depending on the root depth,
yes,
it will go. Yeah, but like the actually maize is the corn, so it goes 70 centimeter or 60 centimeters. So here, we don't know. We need to study.
Yes.
I'm also very new for soil.
Yes, so that's why I see this very interesting to have the vertical profile of the different.
But this is not DGT result. This is the pore water result, because it's quite difficult to collect. Yeah, that's why it's difficult. Mingyue gave me a explanation. It's different to collect the soil sample at different types for DGT, but why she collected sample for the pore water is I need to discuss with her. Yeah, she didn't carry out the DGT types profile for soil. It's just general one. The DGT result I presented, but she's very interested now in apply the DIFS model to add the theoretical part in her thesis. But this is just the beginning of soil DGT application in soil. But I have another PhD will continue, and she planned to cultivate some sample vegetables in the laboratory. Then we want to see what is the correlation. Yeah.
Okay. So thank you. If no one have any questions anymore, then we move. We go on with the next presentation. So please, Martin, you can continue with the next one.
I stopped sharing. Sorry. Yeah.
Trace element distribution in water and sediment of the Nhuệ Đại River Basin, Vietnam. So you will present some result of the previous project.
Yes, thank you. Yes, I'm going to present the results that we got in 2019 in the good old days when we were still allowed to travel. Now we're just sitting behind a computer talking to each other. But we had some quite nice results of this small expedition that we did. We haven't published them yet, but we're working on publications at the moment of this data. So I think you all know this New Day River Basin much better than I do, but just for those who are not very acquainted with it. So the New and the Day rivers, they have their source in the Red River. The Red River is a very large river, which, well, it has a source in China, I think, and it ends into the Bay of Tonkin, I think, more northwards. So you have the Day River, which has a source from the Red River, and which is also regulated by locks. You have the New River, which has also the source in the Red River, regulated by locks. And this New River is receiving the polluted waters from Hanoi City, which has no water treatment facilities. So through different tributaries, it's ending up in the New River. And this New River is connecting to the Day River in this area 3, which we sampled. And also in this area 3, you have some connection again with the Red River. It goes further down to area 4, where there's some other tributaries of the Day River also connecting into it. Further downstream, the river becomes much larger, because there you have an important connection with the Red River, where actually the main water source is coming from the Red River, and then it's ending into this bay. So what did we sample? We sampled in those 5 areas. The area 1, which is upstream of Hanoi, we sampled there the Red River and the New River, just downstream of the lock, but upstream of Hanoi. Then we have the area 2, which is in the Hanoi region, where we took some samples in the New River, only in the New River, and in a couple of ponds, which are very close to this new river. But the ponds were not taking their water source from the new river because the new river is very contaminated at this area. So the number of sampling points is not really very exact because I took this from your previous work. And then in the area 3, we sampled both the Day River. Ooh, my pointer has disappeared. The Day River upstream of the connection with the new river. Then we have the new river downstream of the connection. Again, the points, I don't think they are very correct. And we sampled, there are also different stations on this new river, well, different sites, a couple of 100 meters apart that we sampled. And also 3 ponds in the vicinity of these rivers. So there were ponds in area 2, area 3, area 4, and area 5. So area 4, it was, there you only have the Day River that we sampled, and also area 5, also the Day River, but after the confluence with this, other river, and also 3 ponds in the vicinity. And what did we sample? And how did we sample it? The surface water sample was just sampled using a syringe and a syringe filter. So we took 2 types of samples, one sample we did not filter, we just acidified it. And another sample we filtered and then acidified with nitric acid. We also did DGT water deployments, and that was done in 4 sites, in area 2 in the river and the pond, and also in area 4 in the river and the pond. We used different types of resins. We used Chelex resin for the metals. We used zirconium oxide, which we used for the oxyanions. And we used levatite, which is a resin which has been developed for arsenic, but also for uranium. So it's a very interesting resin. And then we used the mercaptopropyl functionized silica gel resin to specifically measure arsenic 3. And arsenic 3 is a more toxic form of arsenic. And in the sediments, we took bulk sediments at all the stations with Peterson Grab. These samples were homogenized and subsampled, and these subsamples were then taken back. And in area 4, in one of the ponds, we took a sediment core. We just dived into the water. It's only about 3 meters deep, so you don't need any equipment to do diving. And from this core, we extracted pore water with rhizons. And we also sectioned the core to obtain a vertical sediment profile. And we also did some DGT sediment deployments in area 4 in that same pond, at the same place that we took the core. We also deployed the DGT. And then in area 2, we deployed the DGT in the river and the water. No, sorry. In the river and in the pond, of course. It's not water. So we have 3 DGT profiles there. We actually did one in area 4 in the river, but we lost it. So that's very important when you deploy your DGT sediments. First of all, you have to have some kind of buoy that you can find it again when you retrieve it. But you may see that your buoy is not in a place where some rowboat or some other boat can sweep it away. Yeah? So that's quite a problem in the river to make sure that your sediment DGT, you can find it again if there is traffic in the water. So how did we treat the samples? For the water samples, we didn't do any treatment. We just analyzed them as they were. The sediments that were already oven dried directly after the sampling before we took them with us. When we came to the lab here, we sieved them on 1 millimeter sieve. They were grinded and homogenized. And then we did a microwave digestion with 3 acids to have a total digestion, hydrofluoric acid, hydrochloric acid, and nitric acid. And then the hydrofluoric acid was complexed with boric acid so that we could analyze the fraction by ICP-MS. For the DGT, the resins are then eluted, and there's a specific protocol for each resin. I'm not going to give the details for each elution right now. And then for all these elements that were analyzed by ICP-MS. And which elements did we look at? Arsenic, mercury, cadmium, lead, copper, zinc, nickel, copper, cobalt, vanadium, antimony, manganese, barium, tungsten, thallium, bismuth, uranium, molybdenum, strontium, aluminium, iron, titanium. And these were all done by ICP-MS except for mercury, which was measured with the AMA, the Advanced Mercury Analyzer, which is a better technique, more sensitive than the ICP-MS for mercury, and which has better blanks than the ICP-MS for mercury. So what the results I'm going to show, first of all, the total concentrations in the sediments. Then we're going to look at the concentrations in water, both the filtered and the unfiltered samples. We're going to look at the DGT, labile metal fraction, and then the sediment pore water and the DGT trace metal fraction in the pore water, and see what information we can retrieve from those data. So first of all, I'm showing here the concentration of what they call the priority pollutants, the pollutants which are measured in very many monitoring campaigns, so where we can find comparable literature data also, and we can find norms, levels that they should not exceed. So these priority elements are mercury, arsenic, cadmium, lead, chrome, nickel, copper, and zinc. And what do we see? The concentrations of these elements, well, as expected in the New River, which receives all this contaminated sewage sludge, it has the highest concentration. And these are, what I'm showing here is the average concentrations in the different rivers in the different sites. So if we sample 3 sites in area 2, this is the average of the 3 sites. Minimum, maximum, and average concentrations are found below. So in general, if we compare this to this, and these are the Vietnamese water quality guidelines, then we see that in area 2, for arsenic, we are exceeding this Vietnamese quality guideline, and also for zinc. And of course, this maximum concentration observed is also much higher than this Vietnamese quality guidelines. We can also compare them to the TEL and PEL, those are the threshold effect level. These are levels which have been established in toxicological studies. Then we see that for very many elements, these TEL levels have been reached. The average concentrations are actually above these TEL levels, except for mercury, which is relatively low, except in this area 2, and for cadmium, which is also relatively low, except in this area 2. So sediments also give you a much more stable information about long-term pollution, because its concentrations will not change on a daily basis compared to what you can observe in the water column, for example. So you have also PEL levels, probable effect levels, where the concentrations, if these levels are reached, you will have probable effects for the benthic organisms. And here for nickel, for example, in many of these areas, starting from area 2 downstream, you have levels which are actually can be considered toxic. if we compare them also to the sediment quality guidelines of non-polluted, moderately polluted, and heavily polluted, then we can see that for arsenic, the levels are all much higher than what you can consider as heavily polluted, but you have to take into account that the area also has a natural background, higher background level, and that's also why that this Vietnamese sediment quality guideline is also higher, because it takes into account the natural concentration found in the sediment also. So for other metals, it's either moderately polluted, or for some metals can be considered as heavily polluted. So the sediments can still have an important effect on the ecosystem as well. And what we also see is that the Day River, upstream of the connection with the New River, has the lowest concentration of all these elements. We're going to compare these elements with literature data of the same, also Vietnam. It does make sense to compare them to other places. And then if we compare them, for example, to what is found in the To Lich River, this is the river which is actually accumulating all the effluents of the sewage effluents, and then this river is releasing into the New River, then we can clearly see that this river, the To Lich River, is a very important source of these elements to the New River. If you see for arsenic, for example, it goes up to 800 microgram per gram. Oh, I'm very sorry. I don't even, oh yes, it's in the title, microgram per gram. So these are really the source of the elements entering into the New River. It's also, these rivers are also all regulated by locks, and actually when the locks get opened, you have a flushing of the sediment also, which is going downstream. So the sediment as such can also be resuspended and transported downstream, which is has an important impact on the ecology downstream also. So you see it for many elements, lead 300 to 700. This is really what is transported into the New River, and in the New River it's of course mixed with the natural sediment to have these average concentrations. So our concentrations in the Red River are actually comparable to what other river, others found in the Red River as well, and other rivers of Hanoi and New River Basin are actually also, the concentrations are comparable to what has previously been found. So I'm not going to show all the elements, but I'm going to show some typical elements on how they are distributed in the different areas. So we have these series of elements which have a clear, very important source in this New River, in this area of Hanoi. And you see that the New River upstream of this area is much lower. If you go downstream, you see that these downstream concentrations in the New River are affected by the concentrations found in area 2. So you have a clear downstream transport of these elements which sedimentate again in the downstream area and which affect the concentrations of the downstream area. And again, you see here the Day River upstream of the connection has very low concentrations, and after mixing with the New River, you see an important increase in the concentration in the Day River as well. So there's a whole lot of series of elements which behave in the same way because they all have their source in this New River. Then we have some other elements which also have a clear source already in the Red River. So it's also what is transported to the Red River, which affects the downstream concentration. So examples of those are tungsten, bismuth, barium, and what we see for tungsten, for example. So the concentration is even higher in the Red River compared to the New River. And then we see downstream, area 5 of the Day River, where you have this important connection of the Red River with the Day River again, that you see an important increase in the concentration. So it's this downstream transport of this resuspended sediments, which affect the concentrations downstream as well. So for bismuth, this is also very clear. Barium, you have also a series of elements which both this Red River and this New River are contributing to the downstream area. Again, for these elements also, you see that this Day River is largely unaffected, which has much lower concentrations compared to the other two rivers. And the ponds which use the waters of the rivers, they can be affected, of course. They can have higher concentrations due to the sedimentation of the particles when the river water is used. Okay, so these are also other examples of elements which are both in the upstream area. So it's either other pollution sources or natural sources of pollution in natural sources of arsenic here in the Red River, which contribute to the concentrations found downstream. So also for copper, both the Red River and this New River are important sources. So what can we do with these data? We can actually look at how all these elements are correlated and how they are correlated to the sites in which we find them. And this gives us some connectivity between the areas as well also. So we have these elements where we find high concentrations of manganese, tungsten, bismuth, copper, molybdenum, arsenic. And there are also this whole bunch of elements which have high concentrations of all these, also high concentrations of POC, and the most important contribution in this factor is the New River at area 2, which has a very high concentrations of all these elements. And totally at the other side, in contrast to that, is the area 3 Day River, which has the lowest concentration, and the area 4 ponds, and so forth. So actually we can make a dendrogram of these elements to show how the sediment pollution is related to one another, how close the composition of the sediments resemble each other. And then you have on the left side, you have actually the ones with the lowest concentration, so the Day River, and the area 4, the pond. This has an closest to resemble to the area 5 pond, and also a linkage in composition with the ponds of area 4. And the ponds of area 4 are already influenced by the other section, which is influenced by these concentrations found in the rivers of especially the New River and the Red River. So we have this area 2 Red River, which is on its own because it has much higher concentrations than the rest. Then we have this group of area 1, the Red River, and area 2, the Red River, area 1, the New River. So these upstream areas, which has a close resemblance to the most downstream area, area 5, the Day River, because this area 5 Day River has a strong influence of the water flow of the Red River coming into that area. And then we have the area 3 New River, which is of course also influenced by this downstream transport of the pollutants from area 2. And area 2 and area 3 pond, which are closely connected. So these area 2 river has influence on these sites, and then this is also connected with the downstream areas of area 4, which is then also showing influence of the polluted, the downstream transported pollutants. So measuring a large number of elements can actually also give nice information on the connectivity between the sites and how they influence each other. So that was for the sediment section. Now we're going to look at the metal concentrations in the water. And here also metal concentrations in water, they can be more variable on a daily basis. And also, of course, if it's on daily basis, it can have a lot of more seasonal effects also. And what we see here, so these are also a series of elements where this area 2 New River is an important source of the dissolved metal concentrations downstream. And so for chrome, for example, it's very obvious. Area 1 New River for chrome compared to area 3, it has a very important influence of what is coming in from area 2. And this you can see for the other elements as well, such as nickel, zinc, titanium. And so I selected another series of elements to show some other patterns. This is quite interesting because for copper and vanadium, for example, there is an additional source between area 3 and 4. So if this is the area that you're going to sample now, it's going to be interesting to also see if this is repeated, actually, if we see higher concentrations there also, because, well, there are other pollution sources, of course, besides what is just coming in from Hanoi. And this is here, in this case, affecting concentrations of copper and vanadium. So for lead, what did I do? For lead, we also have this Red River as a source. Or here we also have it for copper. Copper concentrations are even higher in there's something above here that now I can't see my slide anymore. Okay, so bismuth, we also have that. Dissolved concentrations in the Red River are almost as high, or here higher than in the New River. So this is actually what is causing the downstream transport. So the sources originating from the Red River itself must also be taken into account, because that's actually also an important water source to the different areas. So if we're going to look at the filtered and unfiltered samples, if we want to compare the filtered and unfiltered samples, I took some examples again here to show some typical differences that we find. So our unfiltered samples, which have been acidified, they give us an acid leachable metal fraction. It's not a total metal fraction. We didn't do a total digestion of the particles. It's just an acid leachable fraction. But you can still already see a very big difference between metals which have a high affinity for particles, so which will be essentially on the unfiltered water samples, the particles, but these particles also include colloids. So for lead, for example, the difference in concentrations between between unfiltered and filtered are very large. So that's a very particle reactive element. Also chrome, it's also typical. It's a very particle reactive. It will bind on iron oxides in the water and on organic matter in the water and things like that. So also zinc, you have a high affinity. So especially here in a new river, you have a very large difference. So this will especially be organic matter binding on particles containing organic matter. So for nickel, it's also clear, but very different from one side to another. So then upstream in the Red River, you have a very large difference between filtered and unfiltered. And in the New River and the Day River, the difference is much lower. So we'll have to look at the physical-chemical parameters that these influence also this behavior of nickel. So we have a whole series of elements which are much less particle reactive, which are much more found in the dissolved phase. And those are essentially most of the oxyanions. So molybdenum, arsenic, tungsten, and to a lesser extent vanadium and antimony, while they're also less particle reactive because they are negatively charged. And at pH 7, most particles and colloids have a negative charge. So there's an electrostatic repulsion already. So they will have less affinity for the particles compared to the trace metals, which have normally a positive charge. We also see, this is very classical, of course, the alkaline earth metals, they don't have a high affinity for particles, they remain in solution. Elements like manganese, you see upstream a very large difference between filtered and unfiltered. And this is due to in oxic waters, you will have a binding as oxides on particles. And when you have more reduced conditions for manganese, you see a much higher mobility of manganese. So in this new river in area 2, and also these rivers in area 3 have relatively low oxygen concentrations. So they have a much higher mobility, much higher fraction in the dissolved phase compared to oxygenated water. And then we can look at what the DGT labile fraction gives us. And what do we see? That the DGT labile fraction is different from site to site and is actually the lowest at area 2. So area 2 has a very high concentration of organic matter in the water, all kinds of organic matter, even oil and things like that. And this will also bind these elements and make them less DGT available. So there will also be less bioavailable, but there is no biota anyway in this water, so that will not really affect the biota since there is not any there. But when these particles and when these, well, not even particles, when these dissolved fraction is transported downstream, it can change the distribution and it can become more bioavailable. So in area 2 in the pond, it's also much more bioavailable for cadmium, for example. Area 4 in the pond and area 5 in the pond is somewhere in between. So also for lead, very low fraction bioavailable, and the least fraction bioavailable is in the area 2 in the river. It's not the case. What's happening here? So for cobalt and nickel, but here we see for nickel, it has a higher bioavailable fraction. And we also saw that the partitioning between dissolved and particulate was also higher for nickel in the previous slide. So these are for the typical metals which we measured with Kelex. We measured much more than these, but I'm just going to show these for the moment. Oh no, sorry, I'm going to show other ones. So we have here what we see for iron, manganese, copper, and chromium. We see a very different behavior of the redox sensitive elements, iron and manganese. So for iron, you have a very low DGT available fraction, which means that iron is disappearing, and probably it's binding to sulfides very rapidly. Whereas for manganese, it stays much more available for the DGT in water. So in these anoxic, it's typical for iron and manganese in the redox profiles also, and in sediment profiles, that manganese remains much easier in solution, even in anoxic conditions, compared to iron, which will have a faster precipitation. So for some elements are quite labile, even in this area. So manganese is practically everywhere DGT labile. The concentration of dissolved are very comparable to the DGT labile concentrations. For copper in some areas as well, in the ponds, you see a good correlation. And here, where there's high organic matter, copper is almost not DGT labile, and also much less in the river downstream. For chromium, when you measure chromium with Kelex, you're specifically measuring chromium 3, and this fraction is very low, and it's maybe even higher in area 2, which can be expected because the chrome 6 form will be reduced to the chrome 3 form in anoxic conditions. And then when we look at the oxyanions, we see that they are much more DGT labile. They also have a much lower affinity for colloids and for particles. We have one problem in area 4 where we have higher DGTs for these 3 elements compared to the dissolved. So there's some problem happening there which we cannot explain. But for the other, you see that it's almost comparable results between the two. I haven't added the standard deviations, but if you add the standard deviations, you see that the two are actually overlapping. And then we also did arsenic. For arsenic, we used different types of resins. We used 2 different resins which are binding all forms of arsenic. And what forms of arsenic do you have in water? You have arsenite, arsenate, so arsenic 3 and arsenic 5, and you also have some methylated forms of arsenic, monomethyl arsenic and dimethyl arsenic. And these are all bound, these can all be bound on resins such as zirconium oxide or lewatite. These are 2 types of resins which have been shown in the lab that they bind all forms of arsenic. So they can be used to measure the total dissolved available concentrations of arsenic. And then we have this one specific resin with mercaptopropyl functionized silica groups, which binds only arsenic 3. It will not bind the other forms of arsenic. So we can make a speciation between the total arsenic and the arsenic 3. Normally in water, the methylated species are in very low concentrations. So you essentially have arsenic 3 and 5, and then arsenic 3 with MPSI resin. And what do we see? Comparing the 2 resins, zirconium oxide and lewatite, we have quite a good agreement between these 2 resins, except in this area 2. In this area 2, so in this highly polluted area. So here we suspect that the zirconium oxide resin is having some problem binding the arsenic, is having some interferences due to the water composition here. Because for the other ones, it works very well, but not here. Whereas this lewatite resin is less affected by this water composition, and gives concentrations which are, well, slightly lower than the dissolved, but not to this extent. What we see when we look at the speciation, arsenic 3 in the pond in area 2, we have quite a high fraction of arsenic 3. So all our DGT labile fraction is practically all arsenic 3. And arsenic 3, you have to remember, is a more toxic form of arsenic. So it can be taken up by the fish also, and this can affect, of course, the concentrations found in the fish. So in the area 1, we have about 20% in the arsenic 3 form, and in a downstream area in the pond, we have quite surprisingly very low concentrations in this pond. And then we're going to look at the sediment vertical profile. So in this area 4, we took a vertical profile. And so this vertical profile actually gives us our historical deposition of these elements in function of the time. And what we see in a vertical profile, that the peaks that we see are actually also correlated to higher amount of organic matter. So it's the transport of organic matter and the settling of this polluted organic matter, which shows increases in the concentration. So some of the elements show also at depth peaks, and this is also correlated to this peaks in particulate organic carbon or also particulate nitrogen, which is settling there. So the ponds are using water of the river to pump into the ponds, and then it can sedimentate, and you can have these different concentrations in function of when the water was introduced into the river. So this sedimentation patterns. And then we did pore water profiles. So with the rhizons, the pore water profiles, oh, I'm sorry, I didn't add the legend, are the blue ones. So this is for iron, manganese, and then the elements cobalt, chrome, cadmium, chrome, nickel, and lead. And we also did DGT vertical profile at the same place. And these are the orange profiles that we see. So what we observe when we compare these two profiles, in the top section, our DGT profiles and our pore water profiles, they match quite well for iron and manganese, and also for some other elements, cobalt, lead, cadmium, for example. Chrome, you have to remember that chrome is only chrome 3 with the Chelex, so it's not giving you total dissolved chrome concentrations. So what does it mean? In the top section, your resupply from your sediment is fast enough so that your DGT concentration is sustained from the sediment. And in a deeper sediment, the sediment also becomes anoxic, it becomes black. So you know there are more sulfides. You'll see that the release of metals from the sediment to the pore water cannot be fast enough to make your DGT profiles match your sediment profile. So there's a restriction in the rate of release from your pore water, from your sediment to your pore water. But from these concentration profiles, we can easily calculate, we haven't done it yet, we can easily calculate diffusive fluxes, because here we have a gradient. We have a gradient from the overlying water to the sediment, and it's actually the gradient at the sediment-water interface which we need to use to calculate benthic fluxes from the sediment to the pore water. So this can be done for all the elements. If the profiles are in opposite direction, if the concentration is higher in the overlying water than in the sediment, then we have a flux from the sediment, from the overlying water to the sediment. Diffusive flux. The flux can always be reverted due to bioturbation and things like that, then we can have release from the pore waters as well. So quite surprisingly that the nickel fraction is much lower than the pore water. If we compare that to what we see in the water, this was quite the opposite. Here we also don't have strong gradients, so there will not really be an important release from the sediment to the overlying water. Also for lead, there's quite some variability, but we don't expect a very important release, diffusive release from the sediment as well. So this is for this this pond in area 4, where we have both the sediment and the pore water and the DGT. That's always the most interesting to have. If you have all the phases, you can make more conclusions than if you only have the DGT itself, of course. So here is a couple of other elements. So all the oxyanions, they have a quite different behavior. We know that they are very related to binding on iron and manganese oxides. So what we see at the sediment-water interface, we have an important release, a subsurface maximum, but it decreases very fast. You have a very fast removal from the pore water in the sediment, and this is different from one element to the other. So antimony is a faster removal compared to molybdenum, and tungsten remains more in solution here, vanadium also. So looking at these gradients, the gradients would be from the overlying water to the sediment. And that's why also DGT sometimes gives much more reliable profiles at the sediment-water interface, because we're never really sure how the concentrations really change just at the sediment-water interface, because we just take one sample above the water and then one sample below the water. So this gradient at the sediment-water interfaces is interesting to study. So here you see an example for tungsten. There is a subsurface maximum, which we probably lose in these profiles because they are not, the resolution is not sufficient to really see a peak at the subsurface. For arsenic, we see a very clear peak, a subsurface peak. So this is related to the release of arsenic from the dissolution of manganese and iron oxyhydroxides. And this is, well, the concentration gradient is much higher than for the other metals. So it goes here from a couple of nanogram per liter to almost 100 nanogram per liter. So there's a large concentration gradient, so an important benthic flux. And for arsenic, we even see that this benthic flux also results in a decrease in concentration in the sediment phase. So you have in this top layer, you have lower concentrations because it's really released from the sediment to the pore water and can diffuse into the overlying water. So these benthic fluxes, we still calculate for this, but we will do this. So for the other sites, we didn't have any cores. We just deployed DGTs, sediment DGTs, in a couple of areas. So in the rivers, in the river at area 2, and in the ponds in area 4 and area 2. So the ones of the area 4 we already explained. So we see this mobilization of iron and manganese at the surface water interface, and for the other ones we don't have any important vertical profiles, so you will have little vertical fluxes. So in the other pond, in area 2, we see comparable profiles. So we have this iron and manganese reduction at the surface water interface, so we can have benthic fluxes of those. For the elements which I showed here, cadmium and lead, there are no important benthic fluxes, so neither in this pond area 2. what we see in area 2 in the river, so this very contaminated one, where there's also no oxygen in the water. We have the same phenomenon that manganese remains in solution, but our DGT iron is extremely low. So it means iron is all removed from the solution.